Our next speaker is Professor Christoph Dellago. He is currently a professor and director of the Erwin Schrödinger Institute for Mathematics and Physics at the University of Vienna. He works on the general area of computational statistical mechanics, which includes rare event simulations, machine learning for molecular simulations, phase transitions and nucleation processes, stochastic thermodynamics, and nanomaterials. Title of his talk is Fluctuating Interfaces and the Bulk Melting of Ice. Christoph.
Thank you very much for the introduction, and of course, thank you very much for including me in this very nice conference, which I have enjoyed very much so far. Of course, it's not like the other one that we had some time ago. I'm talking about the 2017 RARE meeting that we had in Agra. That was really really nice, but very good that you are organizing this meeting online here, particularly because the next time around we can then talk about this meeting we have now, and we will say how much better it is to meet in person than online. But this is the best we can do now, and I'm very happy to be part of it. So thanks for having me. Today I'm going to talk about a little thing that we did, that I did with some people in my group, and with also with Phil Geisler from UC Berkeley. So the work that I'm going to talk about is mainly the work of Clemens Moritz, a doctoral student in my group, and of Maxina Bichler, also a student in my group, and of Marcello Sega, who is now at the Helmholtz Institute in Nuremberg, and also Philipp Geisler contributed. Actually, this was something that we started when Phil was here in Vienna for a sabbatical. If you're interested in what I'm going to tell you, you can, it's all in these two, sorry, I should go to full screen. It's all in these two articles. Now, what I will be talking about is a problem that came up when we studied how ice melts, how water ice melts, and but in particular how it melts in computer simulation with periodic boundary conditions. Turns out that a question that comes up is that of fluctuating interfaces, fluctuating and diffusing interfaces, and it's then relevant to know at which distance the two interfaces touch. Now, so this is the main question that I'm going to answer, and then we'll see how that is relevant for understanding how ice melts. Now, it's known that melting is actually a process that starts at the surface. In the case of ice, we know that ice, even below the freezing temperature, is covered with a liquid layer of water. And this is an observation that was first made by Michael Faraday in the 1800s. Faraday made his famous regelation experiment, where he found out that if you put two pieces of ice together, they freeze together, forming one block of ice. And his explanation was that the ice is covered with a liquid layer, and when this liquid layer that is then put into contact with another piece of ice, then you have ice on both sides of this liquid layer. The liquid layer freezes. This liquid layer is actually the reason why you can make snowballs, why they stick together. Now, the thickness of this liquid layer grows as you approach the melting point, as is shown in these very nice results of David Limmer and David Chandler. And since you have this liquid layer on top of the ice, there is no barrier for melting, and the melting just proceeds from the surface into the bulk. But this is not always the case. There are cases where the melting actually occurs in the bulk, and the first to study this was John Tyndall, actually the successor of Michael Faraday. How he did it was that he took a block of ice and he focused sunlight into the ice, and at the focus, the sunlight heated the ice above the melting. And if that happens, the ice melts at that point and it forms so-called Tyndall figures. You see some of them here drawn by Tyndall himself. They have these very nice dendritic shapes. The particular shape is due to how surfaces grow in ice and how heat is actually transported. Here on the left, you see some more recent figure of a Tyndall figure. What's also interesting is that here at the center you have a bubble of vapor, since the liquid actually has a higher density than the solid. Immediately when you form a cavity filled with the liquid, you have negative pressure, and in this negative pressure a vapor bubble forms. You have cavitation. So there are also other ways to observe melting in the bulk. For instance, if you take a silver nanocrystal and you cover it with gold, which is a higher melting point, then the silver crystal does not melt from the surface, but in the interior. Now, how does this melting occur? Actually, if you want to know how melting in the bulk happens, you have to apply special sampling techniques, and this is actually one of the main topics of this conference. Bulk melting is an activated event because it proceeds via nucleation and growth, and therefore free energy barrier has to be crossed, and therefore the melting is a rare event. So a number of people have studied how melting occurs in the bulk. For instance, in this very nice work of Mark Tuckerman and collaborators, they studied how copper melts by applying adiabatic free energy dynamics and the string method, and they found that there are multiple competing pathways that connect the solid, and here A is the solid with the perfect solid and the solid with a few point effects, and in B here they cluster, and then there is a transition to the liquid. You can go to the liquid via a number of different pathways, and all these pathways involve some defects. Similarly, the melting of ice was studied by Donadillo, RARE2021, and Painello using metadynamics, and what they found is that the transition between the stable states representing the solid and the liquid proceeds via the formation of so-called topologically 5+7 defects. We will hear more about these defects later. Now, if you would like to study dynamical pathways that do these transitions, what you could do is to start them at the transition state and let the system go. But of course, here, as in many other cases, you don't know where the transition state is, and therefore we have all these powerful methods that allow you to study the dynamics of rare events, mechanisms, and rates. Now, but there are cases where you know where the transition state is, and one example is, maybe it's a bit artificial, but one example is the example of melting or freezing at coexistence. So why do you know the transition state in this case? Imagine that you have a system that is at coexistence, and what's shown here is the free energy of the system as a function of an order parameter that quantifies how much of the system is present in, let's say, the liquid phase, and how much of the system is present in the solid phase. Now, if you go from left to right, you go from the liquid to the solid, and the red curve here shows the shows the free energy profile as a function of this order parameter. This could be, for instance, be the number of molecules that sit in a crystalline environment, so that a large value corresponds to the crystal and a small value corresponds to the liquid. Now, if you go, as you go from the liquid to the solid, the free energy goes up and then reaches a maximum, and then it is flat for quite a while. And this flatness here corresponds to the formation, this flat part here of the free energy profile corresponds to the formation of a slab, where some part of the system is liquid and another part is solid, and they are separated by one, or actually by two, flat parallel interfaces. Now, changing the amount of solid compared to the amount of liquid is something that does not cost you any free energy at coexistence, because you don't change the size of the interface, only the proportion of liquid and solid. And since they have the same chemical potential, the free energy profile is flat here. And the height of this free energy barrier is related to the surface free energy. Now, in this particular case, the transition state is known because it corresponds to the slab. It's somewhere here in this region, and in order to prepare, in order to produce a trajectory that goes from the liquid to the solid, what you could do in this particular case, because you know the transition state, is to prepare a slab and then let the system go from the slab. Of course, away from coexistence, the situation is different. Away from coexistence, your free energy profile as a function of this order parameter would look like the blue curve here. And here, even in the case where you have a slab, you have a thermodynamic driving force towards the liquid state, and the system would slide down here very quickly, starting from the slab always to the liquid state. The transition state is somewhere else, and in general, you don't know where it is. But if you have a system at coexistence with periodic boundary conditions, you know that the transition state is actually the slab. So you could, in principle, let the system go from the slab, and this is what you would observe. So here, this is a trajectory where we started in the slab, and this trajectory here happens to melt. The blue particles here are the blue oxygens are oxygens of water molecules that belong to the crystalline phase, and the red ones, they belong to the liquid phase. Now, in other cases, the system will freeze. You see, you have these interfaces, the two interfaces that grow here, and they grow in a way such that the liquid part shrinks. And if you wait long enough, you will end up with the perfect solid. Actually, this solid that we have obtained here is not quite perfect, because a defect is remaining here, and this is a 5+7 defect that we're going to talk about, later. But I would like to answer the question now, to address the question, what can we learn from studying melting or freezing at coexistence? What can we learn by studying this process about the process occurring away from coexistence? Does it have anything to do with what happens if I go into the if I make one of the two states metastate, if I really go away from coexistence? We know that at coexistence, actually nothing should happen, because the nucleation barrier will be infinitely high. But in a finite system with periodic boundary conditions, the barrier is not infinite, and nucleation can occur. But the question is, so what does this nucleation have to do with the nucleation that happens away from coexistence? Let's have a look at this for a simple system, namely for the Ising model in 2D. And the Ising model at 2D without an external field can have a transition from a spin down state to a spin up state. And during this transition, an interface has to be crossed, and how it is crossed you can see here. So this is a, you can see here that this, let's watch it again. Let's start from the beginning. You see that you have a cluster here, the cluster grows, and it grows laterally. It grows in an elongated way until this cluster touches itself across the periodic boundary condition, and then you have this slab, and the slab grows, and it grows slowly because this growth is diffusive, and once it has grown, once it has grown enough, let's speed this up a little bit, then it will actually go down on the other side of the barrier into the other phase. Here on the right, you can see the trajectory in a space spanned by two order parameters. One is the magnetization. So this magnetization tells you that we go from the spin down to the spin up, sorry, to the spin up state. And this parameter D tells us something about the geometry of the cluster that forms. Actually, for positive values, it's the difference, it's the shortest distance of the largest cluster to its closest periodic image. And once a slab has formed, it's the thickness of the slab at its thinnest position. So this is what happens at coexistence. Away from coexistence, so for the Ising model, this would correspond to a situation where you have a field. Something similar happens, but not quite, because you have a cluster that grows, the cluster is spherical, it's much more compact, and then it touches its periodic boundary, and then very quickly it goes into the other stable state. So you have a slab again, and the slab forms and grows, but it forms in a different way when you go away from coexistence. You can see that more clearly here. So without magnetic field, you have this elongated cluster that forms the slab, and it grows until the slab breaks. And with the magnetic field, the cluster stays spherical until it touches, and then it forms the slab much more quickly. So if at all, only the initial stages of this process are comparable in the two cases. Really, the early stages of the nucleation, where you have these small clusters that form, are comparable, but what happens after that is clearly different, and it's a consequence of the periodic boundary conditions that we use here. So what is the limit of size for which you may expect that the two processes are related, are similar? Well, it's the thickness. Imagine the process in the reverse direction. So the size of the cluster is equal to the thickness of the slab when it breaks. And this is the size that is an upper limit for the size of the nucleus at which it still can resemble, can be meaningful for the transition happening away from coexistence. So, and this is the thing that I would like to talk about now. Namely, imagine that you have this slab, and this slab has two interfaces, and these interfaces fluctuate. At some point, the slab breaks. And I would like to understand at which distance this happens, at which slab thickness the slab is likely to break. So let's state this problem more clearly. Imagine that we have two interfaces. The interfaces have average positions, and the distance between the average positions is x. These interfaces, they also fluctuate. And if a fluctuation occurs that is large enough, for instance, here it might occur soon if this interface, this thickness here shrinks even more, then the two interfaces might touch each other. So if I have these fluctuating and diffusing interfaces, then I can ask the question, at which distance do they touch for the first time on the average. And how does this distance scale with system size? So this is the question that we have addressed in this paper here, and this is the question that I will talk about now for a couple of slides. So we can try to understand this in the following way. As I said, the physics of this problem is very simple. The two interfaces, they diffuse and they also fluctuate. Right? So the diffusion of the interface system, which happens through, in the liquid solid case, through the attachment and through the ordering of molecules at the interface. This diffusion is described by a Brownian motion. In addition to diffusion, you have the fluctuations, and the fluctuations, they lead to the disappearance of the slab with a certain rate, and the rate at which this happens depends on their distance. Two interfaces that are close are more likely to touch in the next moment than interfaces that are distant. So how does this contact rate, this rate constant for contact depend on distance? Well, since the fluctuations are Gaussian, it makes sense to assume that this rate constant depends on the distance in this particular way. This is just something that I postulate here. It can be justified, for instance, for particular models of surface growth. But let's, for the moment, assume that I have some rate constant that depends on the position for this for contact, and once contact is made, the slab disappears, and therefore the probability, the survival probability of the slab is proportional to this rate constant. Now, this process can be easily described with a reaction diffusion constant. The U of X and T is the probability density for the distance between the two slabs, and this first term here describes the diffusion of the interfaces, and the second term is a loss term that is due to this reaction, due to the contact. Now, how does the solution of this reaction diffusion look like? It's easy to understand how it should look like. In principle, imagine that you have some position-dependent rate constant here, the k of x, and now I inject particles. I can imagine this, I can view this as the motion of one particle. I inject particles at this x position. Then what first happens, it spreads, and since the k of x is very small here in this region, nothing happens. But some of the particles, they diffuse towards this, the region where k of x grows, and this is where a reaction can occur. The rate at which the reaction occurs is, of course, the density at that point x times the rate constant, and this is a function that is peaked. This function tells us where the reaction is likely to happen. It is peaked because on this side here, nothing happens because the rate constant is so low. And on this side, nothing happens because the contact has already happened, right? The rate constant is large here, so when the system approaches this region here, it will react and nothing is left for the other side. If I'm only interested to know where things happen, then I integrate over time, and this function here, the PC of x, is the probability that the reaction will happen at a certain distance x. Now, how can I compute this probability? This probability that the two interfaces touch at a particular distance x. We can compute this probability using path integrals. We write down the probability of a certain path that survives up to a certain time t, and by going to the continuum limit, you can show that this probability has corresponds to an action that has this particular form. And when you look for the most likely pathway, you find that it's exactly a Newtonian path that minimizes the action, a Newtonian path that lives in a potential that looks like minus the rate constant, the position-dependent rate constant. And for this Newtonian dynamics, there is a conserved energy which has a kinetic part and the potential part, and the potential is just minus the rate constant. And if this looks familiar to you, then probably because this is formally exactly the same problem as the instanton problem in the path integral formulation of quantum tunneling. And the reason is that this equation here is really a imaginary time Schrödinger equation, where the potential energy term actually corresponds to this luster. So this is something that you can solve by minimizing the action and expanding the pathways around this around the minimum action path. This gives you an analytical expression for the probability that contact happens at a certain distance x, and from this probability density you can compute the most likely distance at which this x happens. It's a very simple expression where this w is the Lambert. The w function is the inverse of x times e to the power of x. Basically, for large x, it's the logarithm. And if you compare, this solution here with the numerical solution of a particle diffusing in a rate constant landscape that looks like the gray curve here, then you find these curves here for the probability to make contact, and these are probabilities for different densities. So for different diffusion constants. Sorry, if the system diffuses slowly, then contact happens at large distances because the fluctuations have time to be large enough to make the contact. If the diffusion is quicker, if the diffusion constant is large, then the two interfaces can approach more closely before they touch, and therefore they touch on the averages at smaller distances. This solution here, this is interesting because this tells you that the most likely path has to speed up. The most likely surviving path has to speed up where the rate constant grows, right? Because it essentially falls down into this hole made by the inverse rate constant, and it accelerates here, and the system has to pass this high rate constant region quickly in order to survive. So this is really the same as the instanton in quantum tunneling. Now, in order to really understand how this touching distance depends on system size, we have to apply this theory to a particular model of surface growth. Here we chose a very simple one, the Edwards-Wilkinson problem model for surface growth. If you discretize this model, it's nothing else than a number of Brownian particles that are coupled by harmonic springs. And for this model, you know how the surface roughness, how the diffusion constant, how this prefactor in the rate depends on system size. You know, the scaling from capillary wave theory and from the decay of Fourier modes. So you plug this in, and then you find that you have a very slow growth in one dimension. Is not so slow, it's like a square root of L, but in 2 dimensions, really logarithmic growth that you find of this distance, which means that even if you have a very large system, the distance at which the two interfaces will get into contact is very small. How good is this theory? If you compare it to simulations, you find that it works very well. Here you have results for the 2D Ising model, for the 3 Ising.
Sorry, Christoph. maybe you have to summarize in a couple of minutes, probably.
Yes, I will be done. I will be done soon. So also for the liquid gas interface, liquid vapor interface of Lennard-Jones, it works quite well. So now let's go back, if I may, for a couple of minutes. Let's go back to the melting of ice. So let's look at these trajectories that we start at the for a slab geometry at coexistence, and this is a trajectory where that actually freezes, but it's going a bit slow. I'll speed it up. So you will see that this trajectory will lead to freezing, and all these colors that are shown here denote defects that I'm going to discuss in a second. So what are the defects that can occur? And because I mentioned them because they play a role for melting. You can have interstitials or vacancies. You can have L or D defects. These are defects that violate the so-called ice rules. But then you can also have, and these two types of defects are rather mobile, and then you can have 5+7 defects and more complicated topological defects, where instead of having the usual 6-membered rings, you have rings with a different number of members. For instance, you can have 2 5 rings and 2 7 rings close to each other. This is a 5+7 defects, but you can have more complicated arrangements as well. Now, if you produce trajectories by starting them from the transition state and you analyze them, then you find that roughly you can separate 3 phases of the melting process. Namely, you start with the formation of topological defects. They can be quite complicated. And then in the second phase, L and D defects and interstitials and vacancy pair forms, and they are rather mobile and they move around, creating more defects. And that eventually leads to the melting. It would be interesting to discuss this in more detail. Let me just mention here that in the case of melting, it's not possible to really pin down a specific sequence of events that happen. Actually, there are many different ways in which the ice can melt. All of these but include at some point, of course, the formation of defects. And in most cases, you first start with the formation of these 5+7 defects that are and in later stages, you have the formation of mobile defects. So this basically brings me to the end. I'm sorry for having had to speed up at the end. I will be happy to answer any questions you might have.
Thank you, Christoph.
Thank you.
Yeah, nice talk. Shabuni Tarabdar asked, okay, let me go. So she asked that, how do you take care of the boundary condition for the symmetry of the solid phase?
So, I mean, the simulations that we do here, they are, I mean, we choose a geometry of the box that is compatible with the geometry of the ice lattice. We do the simulations at constant pressure, of course, and that makes sure that ice can actually form. I don't know if this is an answer.
Okay, so Peter is asking that what is the effect of correlation between the surfaces? One would expect that fluctuating surfaces influence each other, certainly when close to each other.
So you mean the correlations beyond touching? This is something that we have neglected in this model, right? So we assume that the surfaces are completely independent from each other. That's of course not true. That's because there will be interactions between the surfaces which are not captured in the model. The fact that the model works rather well indicates that these correlations are not so important, at least not for the question of when these surfaces make contact.
Okay, so Taro Karmakar asked that I'm curious if the transition state definition for a finite size system in the coexistence setup is well defined.
Can you say it again? I didn't understand.
So I'm curious if the transition state definition for a finite size system is well defined.
I think as long as you can define the stable states, then also the transition states are well defined in the sense that these are configurations for which the probability to relax into either one of the stable states is roughly equal. And these configurations certainly exist, and these are the transition states, and this can also be defined for very small systems like the ones that we have studied here.
So, Christoph, my question was more on the finite size effect. Do you see any finite size effects in your...
On what?
Finite size effects.
I mean, in a sense, the whole process is a finite size effect. So I'm not sure exactly what this means. I mean, certainly the transition state that we from which we start here is an artificial transition state that
because more often sometimes you need to take care of this critical nuclear size.
So Tarak, I think this needs more discussion in the possible sense.
I'll write in the chat.
You may continue later with Christoph. And I think Amish wants to ask one question. Amish, go ahead. The last question I will take.
Hey, Christoph, really nice. I wanted to ask a question about the rate as a function of the distance between the slabs. And you assume a parabolic form for the barrier, which I think is certainly sensible. I wanted to sort of make connection to an isomorphic problem of capillary evaporations. You have two hydrophobic surfaces. You have a very similar kind of physics where you're looking at de-wetting between hydrophobic surfaces. And there we've also seen that the barrier varies parabolically, or it's a parabolic function of the distance. Mm-hmm. But that dependence seems to stem from, or to account for that dependency, you assume that line tension becomes important. If you only think about gamma A and PV type terms, then you have a linear dependence, right? And so I was wondering if you could comment on in this particular system where you don't really have an external surface per se, you only have an interface. What might be a line tension equivalent associated with this neck that you might need to form, right, for the two things to come together?
Yes, well, that's an interesting question, right? Because we have, I mean, so the Gaussian form of the reaction rate constant really assumes that the fluctuations are linear. But where you form a neck, you have something that's probably quite non-linear. Nevertheless, I mean, the model seems to work well. But this is something that would be interesting to study. I think you would have to be more careful, because actually you also need to study the statistics of extreme cases. So yeah, I don't really have a good answer for this question, but it's an important question, certainly.
Okay, so let's thank Christoph again for the nice talk.